talk about the lithium-ion battery. There's a principle and their application. So lithium-ion battery now is a big field. Okay, it's a big field, quite important in a lot of commercial device. Okay. And also now, lithium-ion battery, you know, the electrical car, okay, electrical car, it has become maybe for the next 10 years will be dominate the market, okay, in contrast to fuels car. So the battery become very important, okay. So we will talk about the charge and discharge mechanism, and also the energy density, how to calculate the energy density, and the battery materials. We will focus on some of the solid state electrolytes, okay? Solid state, solid electrolyte interface formation. We call it SEI formation, okay? SEI formation. SEI formation in the battery is also quite very important role because the SEI formation has a positive. Positive side, that means which can protect the electrode, because the electrode cover the SEI layer, and this electrode will be not corrosion by the electrolytes. Because you have the, let's look at about this. You have the cathode side and anode side, negative anode side and cathode side. So usually now there is electrolytes, okay? And then once the cathode and anode, they touch with the electrolytes, and this cathode surface will form SEI form, SEI layer, so-called solid electrolyte interface. This solid electrolyte interface for the negative is will handle this diffuse. Will reduce the lithium diffuse because there's a barrier. So lithium need to overcome the SEI. Right? This is negative. Negative means is a minor, 不好的. Okay. But positive is because they are protection layer formed on the cathode or anode. Right? So inside the material will be protected, not corrosion by the electrolytes. Okay. So sometimes SEI is good, but sometimes it's bad. So we have to modulate the SEI thickness. We cannot make it the SEI too thick. If too thick, always bad. Okay. So, and then dendrite formation. Okay. Dendrite formation is one of the issues because the lithium penetrate, transfer to here, copper oxide, so accommodate. So here is discharge, charge, discharge, charge, discharge. So finally, some of the lithium cannot come back. So therefore, as the time goes past, you will see the lithium and lithium will progressively accumulate. So become like a dendrite. You know the dendrite. Dendrite will be very, the mechanical is quite strong. So which will penetrate the electrolytes. Okay. So this dendrite grows, finally making the anode and both sides become shock. Okay, which will explode, 爆炸. Okay, explode. So that's a very safety issue. It's an important safety issue. Okay, important safety issue. So people, they start to think about how to avoid the dendrite formation. Of course, we have to consider how to reduce using some of the anode side and cathode side to think about the material side. But the most important is the separator. Now, the battery, most of the battery are using the electrolytes. It's a liquid state. Just as we mentioned in the chapter 6, there's a dye-sensitized solar cell. We're using the liquid state of the dye-sensitized solar cell, which is liquid. So liquid, we know the ion is transferring liquid is more easy than solid or gel-like. Gel-like, you know, gel, like a jelly, 果冻, okay, like a gel-like, gel-like, 果冻. Gel-like is more chemical stability than liquid state, and then has can avoid the dendrite penetration. And now, even scientists, they develop a solid state, completely solid state. Solid state. Solid state electrolytes, you will make it, you know, more strong. Even the dendrite grows, and then it will be not penetrate. Okay, so and also nanostructural materials. Okay, nanostructural materials, we can accommodate nanostructural materials on the anode side and the cathode side, which can increase the charge and discharge performance. Okay, so we are including this chapter. Okay, this topic. So for the lithium-ion battery, as I mentioned, you know, this is quite important in the future vehicle, especially vehicle. You know, it is the dynamic, right? It's a dynamic. So it is a dynamic. Is a quite the safety issue is quite important. So people want to charge 1 hour or charge 2 hours, and then you can suffer maybe 400 kilo, right? Or 600 kilo, right? So you can fast the charge, and you can extend the vehicle can through over than 500. So that means the vehicle can be suffered from very long time, and then without need to charge, right? So the battery, all of the vehicle, electric car, the performance is determined by the battery, right? By the battery. And also the safety, also the safety. So the grind, you know, the grind scale of the storage for the renewable is also quite important. Still, if we today, vehicle, electrical car vehicle is become popular. For example, the first generation is the Tesla, right? You know, Tesla now is become dominant market. But Volkswagen and also Toyota and also Hyundai and also many Mitsubishi, okay, Volvo, they also develop their electric car, right? But if you are the user, the most important concern is not only the performance of the vehicle car, but also I'm concerned about the charge point, right? The charge point, that means, for example, in the Central, how many charge station, right? How many stations in Central, right? For example, I buy not Tesla, for example, Volvo, and then you have to consider about charging. Right? Today I go to Kenting, right? And where can I find a charge station, right? If there is very less charge station, I cannot go back, right? It's just stuck there. And when you drive a vehicle in the superhighway, you are very scared of when the charge station. I have to find the charge station. So the charge station become very important. Okay, charge station. So this is the most big concern. And also, charge station also depends on the battery performance. If you can say, okay, my battery can suffer 1,000 kilometers. 1,000 kilometers, that's huge, right? So I just need to charge in my home, right? And then I can through in the entire of the Taiwan. I don't need to worry about charge station. So I can have a less charge station. That's okay, right? So battery performance is still one of the challenge that the user need to want to care about that. Okay. So I would say if you are doing such research, battery research, there's no limitation. The device will be always need to higher and higher performance. No limitation, I would say. So one day you might see, okay, the battery can be suffer the higher energy density, and also the battery can be smaller, right? So there's a lot of strategy or topic can do, okay, can do. So this is a working mechanism that based on the schematic diagram, you can see right here. This is a famous materials on the cathode side. We call it positive electrode. Half cell, okay, copper oxide. Cathode, okay, copper oxide. And the right hand side is the anode, okay. Anode, usually you can use in the carbon, right? Carbon, layer by layer, right? So here they connect each other, okay? So as you can see, once discharge, you connect this side. The discharge, that means that the lithium and the copper, lithium will diffuse through the electron and then accommodate on the copper oxide, right? Accommodate on the copper oxide. So as you can see, the copper oxide release the lithium, right? Release the lithium. And then you can see it become the lithium copper oxide. So-called here, the lithium copper will diffuse the lithium to the copper oxide. So the lithium to form the lithium copper oxide. Is that okay? So this is the one reaction we call the discharge. Okay. So in contrast, if we look about another side, okay, lithium copper oxide discharge. Finally, because all of the lithium accommodate to here, finally remain the copper. Okay, copper. So discharge of copper 6 because release the lithium. Okay, and this lithium will diffuse to here to form the lithium copper oxide. Okay, so this is the half reaction, and total reaction is something like that. Get a total reaction. So this is quite simple. It's just a chemical reaction. Okay, and then discharge. Okay, discharge you can see. Once you switch to here, switch to here is a charge. Okay, charge that means lithium copper oxide. This lithium will diffuse back, right? This lithium will diffuse back. So finally, once the lithium diffuse back, because the lithium copper oxide will remain the copper oxide, right? Remain the copper oxide, right? Charge, remain copper oxide. Also simultaneously, right? Because the lithium diffuse back, the copper will form lithium copper oxide. Lithium copper. Okay, copper. So the full reaction, okay, the full reaction looks like that. So now energy density. Okay, energy density is how to do such become smaller and smaller. We call it energy density per size, right? Per size. So energy density you can count usually. If we talk about the energy density, you have the 2 units. Okay, one is calculated by watt per hour, watt hour, and also kg per kg. That means 1 kg per watt per hour. The watt in hour is this is for example 100 watt hour per kg. This energy density doesn't mean 1 kilo can charge and discharge, can storage 100 watt, okay, and then for 1 hour, right? For 1 hour, 1 kg per kg per kg. If we can increase 1 kg become 1,000 watt, that means you get energy density will be increased a lot, right? And also is calculated by size. Okay, size is liter. This is liter. Liter is this area calculated by seconds. So you have this volume meter. Okay, volume. Okay, so you get the difference, but you have usually you have you can count, okay, in difference unit. Okay. So how to increase the energy density is a quite important strategy. Okay, most of the people and scientists they are doing such energy density. So this is the application of the battery materials. Okay, usually you have the electroactive materials. Okay, for example, the carbon. Okay, carbon, graphite, or something of metal oxide. Okay, as well, and then additive with the carbon or some of the polymer binder. Okay, because this polymer binder wanted to making this powder become a paste. You know the paste. Just like a glue, right? So you can coat it on the substrate. You can coat it on the substrate. So you can use the Dr. blender, and then you can coat it 1 layer and 2 layers. Okay, and then you can cure, okay, rolling together. So you have the 1 layer, 2 layers, 3 layers, 4 layers, and so on. So you can get the packaging. Okay, package that. So inside the structure is always looks like that. Okay, you have the separator. Okay, you have the separator, and one side cathode. Another side anode and pack together. Okay, pack together. So this is the anode connect, cathode connect to the external load. Okay, to the external load. So one of the many important issues is the solid electrolyte interface. What is the solid electrolyte interface? Let's take an example of the negative electron. Okay, negative electron. And here is the electrolyte. It's the electrolyte. So we call this as a solid electrolyte interface. Because solid electrolyte interface, that means because of these materials react with the electrolyte and then forming a solid state. So we call the solid state a solid electrolyte interface. Is that okay? Because cathode side or anode side react with the electrolyte and then forming an interface. Just deposit on here. So now is what is the source SEI layer? SEI layer, look here. Conservation layer formed on the surface of the lithium-ion battery anode materials, and then produce the electrolyte decomposition. because of this materials react with the electrolytes, of course the electrolytes will be corrosion, will be decomposed. Otherwise, there's no interface there. Do you understand? Because some of the reaction occur, right? Because reaction occur, therefore the electrolytes will be decomposed. So that means if you have the thicker electrolytes, if you have the thicker SEI, that means your electrolytes been completely react, right? So you have the less electrolytes, the battery cannot function. Do you understand? So that's why you have to control SEI. If the SEI too thicker, that means most of the electrolytes been react with the active materials, okay? And then less electrolytes, the performance will drop a lot. Okay, so the quantity of the SEI played a critical role in the cyclability rate. Okay, cyclability. Cyclability doesn't mean the charge, discharge, charge, and discharge, right? If the SEI too thick, that means the charge and cannot reverse, right? Cannot reverse. So cyclability, rate capacity, irreversible capacity loss. Okay. And safety issue, okay, safety issue. So SEI allow transport and block the electron in order to prevent the further electrolytes being decomposed, ensure to continue electrochemical reaction. So thinner SEI is good. Okay, thinner SEI become a protection layer, and then which can prevent the electrolytes being further react or corrosion. Okay, so that's why I explained sometimes SEI we call it a positive factor. Okay, there is three mechanisms for the lithium-ion battery, most famous. One is the insertion. Okay, insertion, that means insert. Okay, insert. And then alloying. Alloying looks like a reaction, chemical reaction, right? Chemical reaction. Conversion, right? Conversion is also one of the chemical reaction which is similar to phase change. Okay. So for example, let's look about the first step. Okay, insertion. Like a LiC6. Oh, LiC6, you can say 6 carbon, okay, accommodate 1 lithium. So which is forming SEI, not SEI. This is layer carbon, layer carbon. This is carbon. So they react with the C6Li. This is a very famous using the first mechanism, right? Right here, C6. So usually for the carbon, it will using 1 lithium accommodates 6 carbon. Okay. 1 lithium accommodates 6 carbon. The cylindrical capacity has a limitation. Do you know why? Because you need to provide 6 carbon and then only accommodate 1 lithium, right? So the volume will be less, right? So some of the materials, like a CNT, they can accommodate more lithium. Like a later on I will show maybe Li4 accommodates 1 carbon. Li4 accommodates 1 because of the structural difference. Okay, so we need more lithium. to accommodate with the active side. So we call this as the active side. For the alloy, okay, alloy will be more large capacity, okay, which is different than carbon. Because the alloy, you can see, the lithium can be more, accommodate more lithium, and with the metal, okay. And this metal, for example, let me show you. I have to take a note. Just wait a minute. For example, very famous materials that I think you guys understand is the silicon, right? Silicon. Silicon is quite famous. And then silicon, the theoretical capacity can be reached to over 10,000. For example, silicon can be silicon 12. Lithium 12, silicon 7, and then lithium 30, silicon 4, lithium 22. This is some of the composition can be looked like that. As you can see, there's a lot of lithium and then accommodate less silicon, right? Less silicon. So this theoretical capacity will be much higher. But for the carbon, theoretical capacity is about 300 to 400. Later, I will, US slide have a table you can compare, right? You can compare. But for the carbon, is quite, theoretical capacity is lower. But carbon is very cheap compared to the silicon. And then carbon you can always use it, and then without volume expansion. But the silicon, you can see there's a volume expansion in the 400 volume expansion. So it is very poor. Once you can see, for example, today I buy a battery, right? I buy a battery, it's 1 centimeter cubic, for example, 1 centimeter cubic. And then once I charge and discharge, just 1 week, become 2 centimeter cubic, right? This is horrible, right? The size become double, right? So it is the main challenge for the silicon materials. But now, still silicon, because silicon, for the commercial lithium-ion battery, silicon still abundant, okay? Still some of the abundant materials right now for commercialized. And conversion is the metal, okay? It's one of the metal, some of the metal, some of the portion, okay? React with the lithium compound, okay? Later on I will show you, okay? This is still need to develop for the large capacity, okay? We call it conversion, okay? Conversion. So for the first time, okay, insertion and extraction, okay, insertion. For example, the lithium interconnect is an insertion, and then diffuse to here, extraction, okay. And then what is the alloy? Alloy is looks like is a phase change, okay, because you can see this is one size become this size, okay, become this size. So the alloy reaction exists in some main group element, including silicon, antimony, germanium, bismuth, and tin. Okay. For example, tin. I will give you more example about the tin. Okay. Maybe this is in the next chapter. Tin. Okay. Tin will be. Tin can be. Lithium 4.4 is the tip, one tip. This is also possible in germanium. Okay, germanium. So, tin compared to the silicon, theoretical capacity is not quite high compared to the silicon, but it can expand as a less volume expansion. Okay, so we call this metal, okay, all of them looks like a metal, which can alloy with the lithium to form lithium metal. Okay, this M is a so-called silicon, antimony, germanium, bismuth, and so on. Okay, so LiXn again provide high specific capacity. All right. But however, most of them has a high volume expansion, around 300. If you look at about the silicon rich 400 is quite high. Okay, quite high. So that's why the third mechanism we call the conversion, which is using the metal. Okay, most of them. This is a metal, but most of them not quite metal. We can say maybe semiconductor. But for the conversion, you can use some of the manganese and ferrite, copper, nickel. This is the metal. Okay, we call the metal oxide. Okay, metal oxide. So metal oxide typically is you can say this is also one of the chemical reaction, which is the phase transition because the phase has been changed. Okay, phase has been changed. So those the conversion type of material has a relative high theoretical capacity, can be incorporated more than one lithium for metal. Okay, for metal. So if we can accommodate, you can think about that. If this lithium can accommodate to increase, theoretical capacity will be high, right? But if you just have one lithium with the copper 6, theoretical capacity is low, right? Because you have to use the more copper, right, to provide, which means the less side, right, the less side. So that's why usually we call active materials, because we need to provide more active materials for these things to accommodate. Okay. So this is for different mechanism to talk about that. So usually, alloying reaction has a very high capacity. Okay, very high capacity, and then large volume expansion. So you can see like silicon and tin, and less long-term is reversibility because the volume expansion, which means charge and discharge, maybe not you cannot use it for a long time. Okay, so durability will be poor. Okay. Modular capacity doesn't mean intermediate. Okay, intermediate, that's less capacity. Yeah, and then there has a less volume expansion. For interconnection, is looks like a insertion. Okay, insertion. Okay, so there has a less volume expansion, but you can use quite a long time. Although the theoretical capacity is less than alloy reaction, but you can use quite a long time. So it's also quite cheap. Okay, so it depends on the product. Depends on the user. Okay, the user. Some of the user maybe I don't need to high performance, but I am care about how long I can use it, right? So, and some of the user care about the performance should be high density, but you cannot. The lifetime is shorter. So it depends on the user. Okay, depends on the user. So now this example is talk about the tin. Okay, talk about tin. So tin looks like similar to silicon. Okay. If you look about the tin, okay, you can see the tin insertion by the lithium. Okay, by lithium. Charge, discharge, charge, discharge. So finally, you can see the tin will be break. Okay, because you can look at about, for example, this is one of the tin. Okay, and then materials this has been interconnected out, in and out, in and out. So finally, this will be expansion, and then the mechanical strength will become very poor. okay, finally break, okay, break. So because of this, continue to charge and discharge. Okay. So this is the mechanical property. So as a material scientist, you are the famous, you are the material science, I would say, you are the genius compared to the double E, right? Because you know, okay, now mechanical property is poor, so I can add something to the active materials. So become the mechanical property can be good, and then can suffer long time stability, right? So this is the material science genius. So people, they think about, oh, nickel, right? Nickel and the tin. You can see the phase diagram, right? Two binary phase diagram. You can see about this alloy, about the mechanical property, right? There's some database you can search on. So if you look at about that, oh, here, interconnect lithium, charge and discharge, charge and discharge. You can see, because the lithium and the alloy, the bonding strength will be stronger, okay? Will be more stronger, okay? Compared to the single tin, okay? Compared to the single tin. So therefore, this will become more stable, okay? So of course, you can try some of the copper, some of the other materials, and they mix together, and then to produce the active materials. Do you understand? So based on this idea, you have a lot of the selection, right? So a lot of the selection is based on how many literature you have read, or how many knowledge you have, right? How many knowledge. So if you are doing some of the research of such a lithium battery, you should be able to read a lot of paper, not only the performance, but also quite important is how I wanted to use the nickel tin, right? For example, just student asked me, okay, Professor, next week, right? I wanted to get the presentation, right? I wanted to get the presentation. The point is, okay, why you want to choose this presentation topic? The first one I will ask you, what is the interesting point that you want to use, right? So, for example, now if get a topic, nickel tin, and then compare to this, right? Compare to this, oh, here will be suffer long cycle durability, okay? And then I come out another question to ask you, whether it's possible, because this is a literature report, right? This is someone report. And then based on your presentation, I come out another question to ask you, whether it's possible to use some other materials. Can I replace the nickel by copper? Can I replace the nickel by molybdenum? Right? So this is a, the presentation is also one of the parts in this course. Okay, this is one to make sure, because you guys is a graduate student, graduate. Okay, so graduate student, you should be able to correlate all the literature report, and then to finally to correct into one subject, right? Into one topic, which has some of the relative research, right? Some of the relative research. You have to summary. You have to summary and get some idea. Okay? So no worry about that. Just do your best. Okay, do your best. Just something like, okay, Professor, now I have doing some research. For example, I'm doing the solar cell, silicon solar cell research. This is my ongoing research. Okay, and I chose silicon solar cell, and then some of the commercial silicon solar cell just as our course has a report about two dimension, right? There's no surface, there's no high surface to volume ratio, and then for my research, I'm using some doping process, right? And then this doping process indeed can increase the IV curve, something like that. Okay, so anyway, so this is just for your consideration, okay, just your consideration. And for the nickel rich, you can use the nickel rich, okay, nickel rich to do such improvement, okay? Improvement, okay. Time is up. Okay, so let's stop here and see you next week.